So we have exam 3 coming up in 2 weeks. But what I want to do is I want to move exam 3 from November 13th to November 27th.
Thank you.
Okay, that was easy then. No complaints about that?
No.
All right. What that means is exam 3 will include all of chapter 11. But it's just one chapter. Chapters 10 and 11 are Lewis structures. Let's see, and maybe some Lewis structures for acid-base stuff. But
So what are we going to run differently this time around so we're prepared?
So you're prepared. You're going to have to prepare for chapters 8, 9. 9's really short. 10, 11. 8, 9, 10, 11.
Thank you.
8 and 9 are like orbital energy level diagrams, orbitals, this kind of stuff, the periodic table. 10 and 11 are Lewis structures, Vesper, and bonding theory. This little bit of chapter 17 I'm going to squeeze in. This is Lewis structures with the acids and bases. So we're looking at structure and properties here. And what I want to do is I want to switch this. Originally when I had talked about the final, so the 27th, we'll have exam 3. And then I was going to have this comprehensive final exam and then this final exam 2, which is going to be kind of like exam 4. But what I'm going to do is I'm going to have the comprehensive final exam as before. This is going to include all chapters and it's going to be 100% multiple choice. And then on final exam 2, this is 3 hours. On final exam 2, which is an hour and a half, we'll have free response type questions. Free response type questions would be like predict and write the chemical equation for a reaction, that kind of stuff. Or, we haven't gotten there yet, but draw orbital energy level diagrams, fill those with electrons. Or draw a Lewis structure. Actually, I'm going to ask you all those things. Some chemical reactions, some orbital energy level diagrams, some Lewis structure type stuff with Vesper here. And so this is the type of stuff that doesn't lend itself to multiple choice format. Is that clear? I'll probably repeat it several more times. But we're going to move exam 3 to November 27th, which is right before Thanksgiving. All right, then let's continue with chapter 8 today. So yesterday in lab we talked about the solar spectrum. The solar spectrum consists of mostly what type of light? Mostly visible, and then a little bit of ultraviolet, and then some infrared. And so we have the solar spectrum. We can't see, there's going to be a little bit of IR, let's see, infrared, and then we have some visible, and then we have a little bit of UV, solar spectrum. And what we see is we see white light. And what we can do is we can pass this white light through a prism. Or what we call a diffraction grating. To separate it into different colors. And so let's take a look at.
What was the scientist that discovered that it was something Floyd?
The scientist that discovered what?
The prism thing? Oh, it was Pink Floyd.
Oh, Pink Floyd, yeah. Pink Floyd. Wasn't there some? Was the Pink Floyd the PhD astrophysicist guy? The guitar player. That's right. The guitar player decided to get his PhD in astrophysics. Did you hear about?
Actually?
Yeah.
I thought we were. Wait, who's messing with who?
No, that's true, right?
I don't know. He used that for his cover.
Don't worry, it's being Googled. Everyone stop panicking.
Okay, yeah, I'm pretty sure it was the Pink Floyd. One of the band members was really interested in astrophysics and decided to get their PhD in astrophysics. But anyway, here's the prism. And so it turns out the speed of light is the speed of light in a vacuum. But when light goes through matter, it can travel at different speeds. And so as light passes through the glass, we can separate out the components based on slight differences in speed through the medium. And so here we can separate out the colors red, orange, yellow, green, blue, indigo, violet. We can't see the infrared. The infrared would be up here, and the ultraviolet would be down here. But you can have detectors. So if we had a detector here, a detector could be your hand. You could feel, you could feel the infrared. You wouldn't be able to feel the visible light necessarily. Maybe you'll feel the ultraviolet due to burns, after some time. But here, let's see. So we can separate out the components of white light with a prism, and then we can see the full spectrum of light. And so the white light's just the composite. There's another way we can separate it, and that's to take advantage of different wavelengths. So when we look at red light's going to have a longer wavelength. And if it has a longer wavelength, it's going to have a lower frequency. Whereas the violet light has a higher frequency corresponding to a shorter wavelength. So frequencies of light. Okay, based on the wave properties, this gives us an alternate method of separating the light. Where it is. Get this slide here. Here. And that's based on how waves interact with one another. So if I have this wave here, and then there's a second wave here, if they're in sync like this, then they add constructively. So the peaks match and the valleys match. And so what I'm going to do is I'm just going to increase the amplitude of the wave. But if they're out of sync, in this case they're 180 degrees out of sync. That is, this peak here and this valley are now matched. And so if I go positive amplitude and negative amplitude, when I combine those, I get zero amplitude. And so if the waves are mismatched like this, we have destructive interference. If the waves are matched like this, then we have constructive interference. And this mismatch doesn't have to be perfect mismatch. They just have to mismatch slightly. If they mismatch slightly, eventually what's going to happen is it's going to cancel itself out, and we get nothing. And so rather than using a prism, we could use this. Here you can see some interference patterns of the waves interact. But this is a diffraction grating. Diffraction grating has little grooves. This is actually a CD. And in the CD itself are little grooves. And what happens is the light reflects off those grooves. And it depends on the angle of the light and the groove, the spacing of the grooves. And so depending on what angle you look at this, we're going to see certain colors cancel out and certain colors pass through reflection. So it just takes advantage of constructive and destructive interference versus a prism, which takes advantage of something else, the speed. Uh-huh.
So if the wavelengths are in sync, then we'll see the colors of that,
The colors like this.
Yeah. Like what happens when the wavelengths aren't in sync?
What happens when the wavelengths aren't in sync is we get destructive interference, and it cancels out completely. This is something we're going to look at in chapter 12.
That's how AirPods work.
I'm sorry?
That's how AirPods work.
Okay, yeah. Noise cancellation, that kind of stuff, right. But that's with sound waves. This is with electromagnetic waves.
Is it theoretically possible then to build some sort of device that you focus at a beam of light and it like makes it look dark by destructively interfering with the light?
Yeah, something like that.
I'm a super villain. I'm gonna get to work on that immediately.
Yeah, or there are those things that are trying to make you invisible, too, by diffracting. Here, this is it.
Cancels the light.
It depends on the spacing of the groups. These were in sync, but when they bounce off, this bounces off this groove, this bounces off this groove. What's going to happen is it depends on the spacing of the groove. If they're off, like say now they're out of sync, but if they're out of sync by half wavelength, then they're still in sync. But if they're out of sync by less than half a wavelength, then they're out of sync. And so it depends on the spacing here, because this one is going to be delayed. This one's going to go further and then go out here. And if they come out both with the peaks matching and the values matching, then we're good. And so on the spacing, and it depends on the angle that you look at this as well. So this is the whole principle of Bragg's law. Bragg's law is covered in chapter 12. And get to solids. This leads to the technique of X-ray diffraction. X-ray diffraction is a way we can pinpoint where the atoms are based on creating layers of atoms. And so this is Bragg's law in action. We create layers of atoms and then see how the light diffracts off there. The light that diffracts off these are X-rays. X-rays have wavelengths around an angstrom so that they can interact with the atoms.
Wait, so individual atoms can be said to have a specific place in time, but individual particles can't?
Individual atoms, yeah, can be pinpointed
Huh.
in space.
Within like a range or within a point?
Because the atoms themselves are kind of massive compared to electron, we can pinpoint them. The electrons cannot be pinpointed, though. Actually, let me take that back. Electrons can be pinpointed, but if you pinpoint where the position of the electron is, then you lose the information about. So it's one or the other. This is called the Heisenberg uncertainty principle. Yeah, so we'll look at that too. This chapter. Anyway, we can separate it into the components here. And then what we do is we just see, what colors or what wavelengths of light, it could be infrared, so there's no colors, or UV, what wavelengths or what frequencies of light interact with matter. Well, not everything will. I mean, let's say your matter absorbs all these colors. If your matter absorbs all these colors, then what color will it appear? Black. And so we have things called black bodies. Black bodies absorb all colors. They appear black. If they don't absorb any of these colors, what color does it appear? White, or colorless. So what we're going to do is we're going to look at black bodies. Why would something absorb all those colors? What happens when it absorbs? Actually, this isn't more. This is a prism, or you could build little mini prisms using water droplets here. Make a rainbow. So what black bodies do is black bodies will absorb all colors, or if you get them hot enough, excited enough, they'll emit all colors. Look in the center here. Do you see what color that is? White. And so this is what we call white hot iron. molten iron. Molten iron's a black body here. And in this case, it's not a black body absorber, it's a black body emitter that is emitting all colors. The sun is like a black body emitter too. And so what is absorbing and emitting the light? Well, it's easy to make a black body emitter. I can do that here. These matches got wet.
Like what? I got like 26 letters about. Oh, a lighter? Oh, yeah, what? No, this is funny. I also don't think I'm supposed to have a lighter.
Why do we use matches?
Oh, wait, why did you ask me?
Those buttons. So why do we use matches instead of like those?
The strikers? I don't know. We used to have strikers. But I think it was based on cost. You know, because we would have to replace the flints in the strikers.
Also, people would just steal them constantly. It's cheaper to replace
Well,
a box of matches.
We had the strikers tied to the plumbing
Oh, that's
here,
very
so
funny.
people couldn't take them. So
But in biology we don't.
theft wasn't an issue.
That's sweet.
I don't know. Yeah, let me just grab a match. Yeah, if somebody, I think, you know, a lot of people like to play with the strikers and then just like you get the sparks and stuff. So. Kept striking. So the strikers, the flints didn't last very long at all. When you shut these off, don't shut them off with the needle valve. This thing, the needle valve on this thing's jammed into the seat, which causes a dent in the needle valve, and it's harder to fine tune the flame. So when you get a flame, you need to get a cone on this, otherwise it just doesn't get very hot. And so we always try to get a cone. Even if it's small, it's better than no cone. A big flame with no cone versus a small flame with a cone. A small flame with a cone is better. So let's, I'm going to do a black body emitter. I don't know if everybody can see this, but so if I remove this now, is it glowing? It's not glowing, but do you know I feel the heat? I can feel the heat radiating off the metal. What kind of radiation is that? Infrared. So you can feel the infrared. The infrared's causing my atoms in my skin to vibrate more. But now, do you see it glowing? It's glowing red hot. Do you see that? Red, orange, yellow hot. That's now you see photons of what? Red light hitting, moving at the speed of light to your eyes, so you can see that. This cools pretty rapidly. Eventually, I could get this glowing how hot? White hot.
I was going to answer degrees.
What's that?
I was going to answer degrees.
Oh, okay. It's going to be extremely hot. Stainless steel has a pretty high melting point. Iron, that stuff will melt. before. But it's glowing white hot there, so they're getting it hot. So if we have a black body emitter like that, what's happening? Like this, or the sun, the sun is glowing white hot. So what's happening there? What's happening there is, let's say we're heating this metal up. When we heat this metal up, then it gets hot. As it gets hot, the atoms start to vibrate. But not just the atoms, because the atoms are going to have the nucleus. So the nucleus is going to be vibrating. But in addition to the nucleus vibrating, the electrons are going to start vibrating, or at least oscillating or doing whatever. And so as these electrons get excited, they don't stay excited forever. So eventually the electrons are going to drop down in energy, and they're going to emit radiation because energy is conserved. And so in the sun, you have these high energy electrons, and those are going to be emitting light. The same thing here. We just heat this up. And so the sun is an excellent source of white light, and also metals. Metals can give off white light. And so the old incandescent light bulbs, these LEDs are different, but the old light bulbs, they used a metal. Stainless is kind of expensive. They used a metal that has a very high melting point. Do you know what metal they use in incandescent light bulbs?
Tungsten.
Tungsten. Tungsten's melting point's over 2,000 Celsius. It's really high. And so they can heat it up to white hot. But the problem is when they heat up tungsten, tungsten is easily oxidized. And so if you start heating up the tungsten, it's going to oxidize pretty rapidly. When tungsten gets oxidized, it forms tungsten oxide, one of the tungsten oxides. Tungsten could be, if you look at tungsten.
That's why we put it in a noble gas tube.
Yeah. Tungsten, the max is 6. And so we could form up to tungsten 6, but it could be tungsten 2 oxide, tungsten 4 oxide, or tungsten 6 oxide. Those are typical. But the problem with tungsten oxides is they don't conduct electricity. Actually, let me back up one step. I don't have to use a flame to heat up the metal. Do you know another way to heat up the metal? The other way of heating up the metal is passing electricity through it. When you pass electricity through it, the atoms are vibrating, and that causes resistance. So as the electron tries to go through the metal, it's meeting a lot of resistance by these vibrating nuclei. And with that resistance, energy is lost in the form of heat, and so the metal is going to get hot due to the electrical resistance in there. And so I could heat the metal using a flame, or I could heat the metal using electric current. In a light bulb, in a regular light bulb, we heat the metal using electric current due to the resistance. And as that metal gets hotter and hotter, it will start to glow. First it'll glow infrared hot, then red hot, then etc. until it glows white hot. But you have to protect it from oxidation by encapsulating the tungsten in an inert gas. What gas do they use? Do you know what gas they use in light bulbs?
Many.
Yeah, they can use many.
Usually halogen almost always.
The halogens are put in there for a specific reason.
Oh, because they don't react.
No, the halogens react. What happens is not only do they start to glow, but what happens is when you heat the metal very hot, it vaporizes the surface atoms. When it vaporizes the surface atoms redeposit on the inside of the glass. When they deposit on the inside of the glass, you lose intensity. The light bulb gets dimmer and dimmer. And so what the halogens do is they scavenge the metal atoms that are deposited on the glass surface and redeposit them on the filament. It's really weird, but there's some gas chemistry that happens with that.
Weird.
And so, what happens is light intensity decreases over time continuously, but with a halogen, it stays fairly constant until eventually it'll die. But we can make a black body emitter. In fact, that's what we want. We want a black body emitter so we get nice white light, like the sun. So let's take a look at black body radiation. Actually, I need to do... before I do this, let me talk about visible light a little bit more here. And light. So we want to know, even though the visible spectrum is kind of a small portion of the electromagnetic spectrum, we want to know some key or significant reference points of the visible spectrum. And so let's go from shorter wavelength to longer wavelength. And so we'll put red, which is the longest wavelength, orange, yellow, green, blue, indigo, violet, like this. Okay, so a couple of things we want to know. One is the border. You know, where does red end? At what wavelength? Do you know? The range of wavelengths? 760. And so here at 760 nanometers, that's the edge of red. If we go beyond 760, like say we're at 1,000 nanometers, at 1,000 nanometers, what type of light would we have? What's beyond red? Infrared. And so this would be IR, infrared radiation here. At the other extreme, we have a border of 390 nanometers. And this would be the edge of violet. And beyond violet, what type of light would we have? Ultraviolet. So let's say we're at 350 nanometers. What kind of light is that? Ultraviolet, etc. 200 nanometers would be ultraviolet light. Now, there are two types of energy that we worry about. I'm jumping ahead and back and forth. Do you know one of them is the total energy. The total energy is going to be related to the intensity of the light or the amplitude. And what it equals is it equals the sum of the photon energies. And so the other energy that we worry about is the photon energy. The photon energy is equal to the energy of a particle of light. This is not a particle in the sense of an electron or a piece. It's a particle in the sense of it being a packet of energy, light energy. And so it's a particle of light energy. It has no rest mass, though. So there are a couple of things to better understand the light here, because it's a little bit weird. And so we're going to look at the photoelectric effect first before.
Do we have a demo for this?
I'm sorry?
Do we have a demo for this?
The photoelectric effect? No. Do they have one in physics?
Oh, I don't know.
No. They might. So when we look at Einstein, did Einstein win the Nobel Prize for E equals mc squared? No. You know what Einstein won the Nobel Prize for? The photoelectric effect. And the photoelectric effect is thinking of particles of light or photons of light. And so we'll just call it photons of light. And these photons of light come in packets. These packets are h nu, which is equal to hc over lambda.
So it's a U.
No.
Mu
Oh.
or nu. Actually, this is nu, which is equal to the frequency. Nu. So let's talk about the photoelectric effect here. Let's say I have a 100 watt light bulb. You know what a watt is?
Joules per second.
Yeah, a watt is joules per second. So I have 100 watts of X-ray radiation. Means I have 100 joules of X-rays per second. And then I'm going to have 100 watts of red light. All right, so that's fine. This is 100 joules per second. This is 100 joules per second. And so it appears that both are the same. So what difference does it make? If you have 100 joules of X-ray and 100 joules of red light, they have the same energy, don't they? It's 100 joules per second of light energy. So it's the same energy. If it's the same energy, then we're fine. Right? You don't need any shielding. Maybe you only need shielding, you know, when you get to maybe 1,000 watts or 2,000 watts. Is that correct? But if I just have 100 watt, it's like a 100 watt light bulb. I shouldn't be afraid of X-rays, right? Or let's say if you had 100 watts of gamma radiation, should you worry? No, I mean, a lot of people have 100 watt light bulbs at home, the incandescent ones. Now you got LEDs, which take a lot less, but they're equivalent to 100 watts, or can be equivalent to 100 watts. And so do you have to worry? You probably said it's not a big deal. I mean, 100 watts is not a big deal, right? This is one of the arguments. Somebody was making this argument for Fukushima radiation. They said, don't worry about the radiation. It's only like 100 watts. You take 100 watts, 100 watts is so little, isn't it?
Of work.
Huh?
Of work.
No, of radiation.
No idea what the box is.
Let's put it this way. What if I had 100 watts of red light and only 10 watts of X-rays? What would you rather be exposed to
X-rays.
unintentionally? 10 watts of X-rays. Oh, 10 watts of X-rays, that's less energy than 100 watts of red light. Is that right? And so that brings up a point. You know, the analogy the person was using likened it to this. If you have, let's say, and this was kind of how the analogy went, but I don't remember the exact wording of it. But if you have a bullet, and a bullet has some energy, but if you take that bullet's energy and distribute it amongst everybody in the stadium, then the amount of energy that each individual person would be exposed to is extremely small. So if you had like a bullet of gamma radiation and you distribute it over, let's say, 20,000 people, then it's negligible, right? It's negligible, the amount of energy. But the problem is unfortunately that bullet is not going to be distributed amongst 20,000 people. That bullet is probably just going to find one unfortunate victim.
Depending on the caliber, maybe 2 or 3.
I don't know, but what the caliber? I mean, it could be.
Some people got that joke.
And so the problem is that some people were thinking in terms of this. Well, it's 100 watts of gamma radiation, no big deal. 100 watts of gamma radiation, 100 watts is not that much, 100 joules per second. Right? But that doesn't seem to make sense, does it? And so there's something that person was missing. And that something that person was missing was that this. We have to visualize this, 2 energies. 100 watts is what we call the total energy. And it's important. The 100 watts for sure is important, because if it came down to 100 watts of gamma radiation versus 10 watts of gamma radiation, I'll take 10 watts of gamma radiation, because it's a lot less radiation exposure. I used to work with radiation. I used to carry a radiation badge,
Wait, where did you work?
I used to work with X-rays. And what's that?
You see green, you get mad.
I'm sorry?
Do you see green, you get mad?
No.
Gamma rays.
Yeah. Right. Right. Yeah, the funny thing is you wear a little radiation badge. Inside the radiation badge is a piece of photographic film. And so what they do is every month you turn in your radiation badge, and then they develop the photographic film to see how much radiation you were exposed to. If you got exposed to way too much radiation that month, then they prevented you from working the next month. But it's like, it's after the fact. You want to know, am I being exposed to too much radiation right now? I want to know so then I can leave the room. But unfortunately, it's like, oh, wow, you got way too much radiation this month. You need to not go into the lab next month. That kind of
I really
thing.
wish that was every day.
But they have real-time detectors that you can hear click off. That's a lot better than these little photographic badges. Fortunately, I never exceeded my radiation dosage. But I also got out of that. I mean, there are people working with gamma emitters, and they had lead bricks set up and stuff. And they'll have a badge like that, but if you're working with gamma emitters, I'd rather have something real time. That way because you can be exposed to way too much. It's like the guy who stuck his head in the particle accelerator. He'd want something real time to tell him, wow, get
I
out.
think that was the blinding light in his left
You're
eye.
right, that flashed. Yeah, that was crazy. Unfortunately, he didn't make it, did he?
Well, he lived for like 3 years. I mean, I think saying he didn't make it is a bit. I would say that he died due to the failure of the Soviet healthcare system. If he was an American, he would have lived.
Well, I don't know. It was excruciatingly painful, I heard.
Really?
Yeah.
I can imagine.
I don't think, that, lived is, yeah. And so what we have to do is we have to look at something else. So if we look at X-rays, they have shorter wavelength, whereas red light will have much longer wavelength. This. And so what we have to do is we have to look at the photon energy. There's a big difference in the photon energy. The photon energy for X-rays is much, much greater than the photon energy for red light. And that depends on the wavelength, because you got to remember that E of the photon is equal to h nu, which is equal to hc over lambda. And so if lambda is small, short, then the energy is large, versus over here, E of the photon is equal to h nu, which is equal to hc over lambda. Lambda is much bigger, and so the photon energy is much smaller. And so the other way we visualize this is this. You know, this would be like baseballs. Let's say we have baseballs, and these baseballs are coming at us 80 miles an hour, or what they do in games, 80, 90, 100 miles an hour. Let's say it's coming at us at 80 miles per hour. Over here we have ping pong balls. They're traveling at the same speed, 80 miles an hour. And so a baseball versus a ping pong ball. What would you rather be hit with? A ping pong ball going 80 miles an hour, or a baseball going 80 miles an hour?
Neither.
Well, neither, probably, but if you had to, you'd probably get out of there, but a ping pong ball would cause a lot less damage, wouldn't it? But we need it to have the same total energy. In order for it to have the same total energy, we have to increase the amplitude. That is, the only way we can increase the amplitude is by adding more ping pong balls. So what we need is we need a lot of ping pong balls here to come up with the same total energy as a few baseballs. And so then we'll get a total energy the same here. So this would be like, okay, if you get hit with a tidal wave of marshmallows versus getting hit by a tidal wave of water, you know, marshmallows wouldn't cause nearly as much damage. And so this is the same thing, but they have the same total energy. So when we're talking about 100 joules or 100 watts and 100 watts, 100 joules per second, 100 joules per second, then what we have to do is we have to look at the individual photon energies to see. And so, and then what we do beyond that is, okay, we have to look, you know, if we have a baseball over here, that baseball is going to concentrate much more energy if you get hit by one than one ping pong ball. And the thing is it possible to break up the baseball into smaller pieces and then distribute that baseball's energy? Let's say, you know, a ball hit and then hit one of the people in the grandstands. Can you distribute all the energy of that baseball amongst all the people in the grandstands, or is it just one victim that gets hit? It's just one victim that gets hit. And so what this person was trying to do with the gamma radiation was they were trying to say that not one person gets hit by the gamma radiation. We're going to distribute that gamma radiation amongst all the people, and therefore it's not bad. Uh-huh.
Okay, you and I both, Mr. Wrong, but you're not going to believe this. He's currently alive.
That guy's currently alive?
He's living now. He finished his doctorate.
Oh, I thought
That's
he had passed
crazy.
away. That is crazy.
That's
Okay.
crazy.
Well, then that's a big plus for Russian medical system.
Kind of, yeah.
Yeah. That's really good.
Can you imagine that happens to you when you don't even get any superpowers? I'd be so disappointed.
Yeah, that would be pretty
You can't
disappointing.
shoot proton beams from your eyes or anything? So.
All right, so the next thing we're going to look at is the photon energies. So at the limit here, I'm going to calculate the photon energy at 760 nanometers. And so what would the photon energy at 760 nanometers be? And the photon energy is just going to equal h nu, which is equal to hc over lambda. All right, you don't have to memorize h. H is Planck's constant. It's 6.626 times 10 to the minus 34 joules times seconds. C is the speed of light, which is 2.998 times 10 to the 8 meters per second. So this is Planck's. Planck's I don't think has a C. Planck's constant and speed of light. So those will be given, as will this equation. I'll just give you this equation here. And so what does it come out to? So we go 6.626 times 10 to the minus 34 joules times second. A joule per second is a watt, and that's related to power. A joule times a second is called action. And so it's kind of a weird unit. It's a unit of action. So we have this joules times seconds times the speed of light, 2.998 times 10 to the 8 meters per second, divided by lambda. We have to write lambda in meters, so that's 760 times 10 to the 9 nano. Nano is times 10 to the minus 9. Micros times 10 to the minus 6. Nanos 10 to the minus 9 meters. Some people like to convert this into 7.60. If we move the decimal 2 over, then the coefficient goes smaller. This has to go bigger, so it goes to 10 to the minus 7. And so typical wavelengths of light are the hundreds of nanometers, or the hundreds of times 10 to the minus 9 meters, or in the single digits of 10 to the minus 7 meters. Uh-huh. Yes. Just converting from nanometers to meters. That way we get the units to cancel out, and then what do we end up with for the energy of a photon?
So this is chapter 8?
Yes. Does somebody have it? Okay. I got that 2.613 times 10 to the negative 19, so it's within round off. 10 to the minus 19 joules, is that very much?
10 to the negative 19? No.
No, that's nothing. How much water can you heat with 10 to the minus 19 joules? Would you be able to heat any water?
Probably a couple atoms.
No. Yeah, a couple of atoms maybe. Yeah.
Like, 'cause Avogadro, what?
Right. Well, how about a violet photon? And so at the other limit, we're going to look at E of the photon at 390 nanometers. So this is going to be equal to hc over lambda. And what do we get over here? So h is 6.626 times 10 to the negative 34. C is 2.998 times 10 to the 8th. And then it would be 390 nanometers. A nano is 10 to the minus 9. And I get 5.093 times 10 to the minus 19 joules. Is that much energy? No, not at all. But the problem is we work at two different scales. Joules or joules per photon. So this is just one single photon. And so this would be joules or joules per photon, because that's what we're calculating, the energy of this photon. The other energy that we look at is, what if we had a mole of these photons? What if we had a mole of photons? Then what I'm going to do is I'm going to go 5.093 times 10 to the minus 19 joules per photon times 6.022 times 10 to the 23rd photons per mole of photons. And so I'm going to multiply this by Avogadro's number. And I'm going to get 306,732 joules per mole, or 306.7 kilojoules per mole. Yeah. The question might not tell you to, but sometimes you have to, because of the information that's given in the particular question. So what we want to know, actually, we don't want to know both of these. We want to know one or the other. There are two energy scales that we look at. One energy scale is the energy of an individual photon of violet. This would be the highest energy violet you can have. You can have lower energy violet light with longer wavelength. This would be the lowest energy red we have. You can have a little higher energy red with shorter wavelength this way. But these are the limits. And so it's easier to remember, maybe in kilojoules, this is about 300 kilojoules per mole of light. And then over here at the other end of the spectrum, what would it be? So I'll just take what I had, 2.613 times 10 to the minus 19 times 6.022 times 10 to the 23rd. And so this is adding. You know, 2 photons would be double that. 3 photons, triple that. An Avogadro's number worth of photon would be an Avogadro's number times that, which is equal to 157.3 kilojoules per mole. So visible light ranges from this is a number I don't remember. I just remember 10 to the minus 19. From about 3 to 5 times 10 to the minus 19 joules per photon. Or, this is probably more practical, 157.3 to 306.7 kilojoules per mole. So what can you do with that kind of energy? Well, you can do different things. For example, you could, I know I said that what type of light is required to break bonds? UV. UV light is required to break bonds, but what if you had really weak bonds? If you had really weak bonds, could you use visible light to break those bonds? And the answer is yes. So for example, these are the bond energies. This is how much energy in kilojoules per mole is required to break bonds. So if you look at iodine, could you break iodine bonds with visible light? Yeah. So therefore, if you ever buy iodine, iodine is stored in black or brown bottles. Why do they use black or brown bottles to store iodine? So the bottle absorbs all the visible light, so it doesn't make it all the way to iodine. If you stored iodine in a clear, colorless bottle, you're going to destroy it all, because the light from the light fixtures will break all the bonds here. What else do you have to store in brown or black bottles? Hydrogen peroxide, because look at the peroxide bond. A peroxide bond breaks at 146. That's almost what? 146 is not even visible. 146 kilojoules per mole is what type of light? Infrared.
Let's go.
So all it takes is one big vibration and the bond's broken. It's infrared light will break. And so hydrogen peroxide is not thermally stable, and it's not stable to visible light. It's got to be protected from light. Otherwise, those bonds will break. Whereas other things like nitrogen triple bond, that's 941. That's going to require a lot more energy than visible light to break. And so we have to worry about certain things here. Carbon-carbon bonds, 348. What is that? 348 nanometers? Kilojoules per mole will be in what? Will be at what? Part of the electromagnetic spectrum. People are concerned about carbon-carbon bonds because you have lots of them. You have lots of carbon-carbon bonds in your body, and so you probably should avoid exposure to what type of light which will break those bonds. 348 kilojoules per mole. .348 kilojoules per mole must be, well, pass up violet. So what's past violet? Ultraviolet. So it's going to be ultraviolet light. And so you want to avoid that. Now, what we're going to talk about here is the photoelectric effect. Again, I'm going to come back to it here now. And what the photoelectric effect is using light to ionize metals. And so what metal should be easy to ionize, you think? Group 1 metals. Yeah. A group 1 metal like lithium, potassium. Let's look at potassium solid here. And so I want to use some light to do this. And the situation is this. I can put some red light here. And is red light enough to ionize the metal? It turns out it's not enough. If I shot a photon of red light here, nothing happens. It's not enough energy to eject an electron, so no ionization occurs. So what I'm going to do is I'm going to increase the energy of the red light. How can I increase the energy of the red light? Well, rather than having one photon, I could have like a mole of photons. Or rather than having a mole, I'll just call it 100 watts. And so I'll bump it up. I'm just going to increase the intensity of the red light. And so if I go to 100 watts, you know what happens? Nothing happens. No electrons are ejected. So I'm not going to give up. I'm going to go to 1,000 watts. Surely, if I go up to 1,000 watts, will I ionize?
Is that when my purple lasers die way faster than my red lasers at the same brightness?
Actually, I'm not sure what the laser, I'd have to look at that. But off the top of my head, I don't know why. Could be. How many watts is your laser? And so 1,000 watts is going to have much more amplitude, much more intensity. Will I get electrons ejected? No. Still no electrons are ejected. I'm going to go up to 100,000 watts. If I go up to 100,000 watts, will I have electrons ejected? No. Still no electrons are ejected. And so no matter how much I turn up the power to this, no electrons are ejected. That's because red photons are like ping pong balls. These ping pong balls, even if you have a tidal wave of ping pong balls, nothing's going to happen. So what we need to know is we need to know what kind of light will ionize potassium. And so let's just do this as a sample calculation here. What wavelength of light is required to ionize potassium? So I have to look up something called the ionization energy. When I look up the ionization energy for potassium, the ionization energy of potassium is 419 kilojoules per mole. The ionization energy is technically for gaseous atoms, but I'm going to just apply this to solid. So what this means is if I have 1 mole of potassium ion, then I'm going to try to shoot photons at this.
What did you do?
I'm sorry? What should I do? Now, technically, this ionization energy is for gases, but I want solid, so I'm going to put solid here.
So is that kilojoules, HJ? What is that?
KJ, kilojoules, yeah. So we have quantum stoichiometry here. Let me talk about quantum stoichiometry for a second. In quantum stoichiometry, if I have a mole of potassiums and I want to ionize them, can I just hit them with one megaphoton, like some megaphoton?
Now you speak more language.
So, for example, you know have you heard the
Dragon Ball Z, yeah.
have you ever heard of the kill one bird or two birds with one stone? Can you kill two birds with one stone? I don't condone killing two birds or killing any birds, but if you had to, let's say you're starving and you needed to get two birds, can you kill two birds with one stone? Maybe if you're good and the stone goes through one bird and hits the other bird, maybe that works. But in quantum, it can't. Let's say you're kind of weak. If you're kind of weak, and can you just take, rather than one weak stone, can you take two weak stones and cumulatively have those two weak stones hit the bird? And no, that doesn't. And so in quantum stoichiometry, it works like this. If I have one potassium, I need one photon. It's like saying, okay, I'm actually really hungry. I want to kill every bird in the U.S. with one stone. How big of a stone would that have to be?
A meteor.
asteroid?
Yeah.
It would have to be like an asteroid, right? It would have to be
Actually,
like
the universe
world-ending
survived.
photon. This photon would annihilate the universe.
Sure.
But you know, in Chem 1A, people try to do this all the time. They try to kill Avogadro's numbers worth of potassium with one stone. And how big is that stone? Well, then I asked them to put it on the electromagnetic spectrum. When they put it on the electromagnetic spectrum, they see, well, gamma ray ends here. So what's beyond gamma rays? You know? And they're like orders and orders of magnitude beyond gamma radiation, you know, at least at the limit. I mean, there's a certain limit of how much energy you're going to have before things start to.
Yeah, how energetic can a single photon be?
If you have some kind of photon that's like that, I don't know, that would be one of those like photon torpedo type things or something.
I've never heard of that in my life. You have to tell me.
But anyway, so quantum stoichiometry works like this. If you have one bird, the potassium, you need one stone, one photon. And so if we want to ionize a mole of potassium, I'm going to need a mole of photons. And that's going to give me a mole of electrons here. And so it's probably better, rather than doing this per mole, it's probably better to do this by atom. So if I have one atom of potassium, then that's going to require one photon, which we call h nu for short, because and so this isn't so easy, because normally, do you think every photon is going to hit its target? Do you think some photons are going to miss? And the reality is some photons will miss. And so this is assuming 100% quantum yield. 100% quantum yield means that each photon hits its target. Probably in order to ionize a mole of potassium, we're going to need a lot more than one mole of photons, because a whole bunch of these photons aren't going to make it. You know, some of the potassiums are going to be buried in the lattice, the solid lattice. They're going to be in the shade and not necessarily exposed to the photons. But this is what we're going to assume. We're going to assume we're going to have 100% quantum yield. Each photon will hit its target. And so a big mistake comes here. Let me show you. if I need 419 kilojoules, then what some people do is they go, okay, I got E of the photon equals 419 kilojoules, which is equal to H nu, which is equal to hc over lambda. And then they solve this equation for lambda, and what did they just calculate? They calculated the wavelength of this universe annihilating photon, the photon that's going to kill every single bird in the sky in the US, right? This is the asteroid of photons. We don't want this. Instead, what should I have done? Instead, what I should have done is this. So this is wrong. What I need to do is this. If I have 1 mole of potassium, then I'm going to need 419 kilojoules worth of energy to ionize, to make potassium an electron. That 419 kilojoules is going to go to 1 photon or a mole of photons? A mole of photons. So this has to be distributed amongst a mole. And so this is E total. E total, what I need to do is I need to think in terms of atoms. So if I have 1 potassium atom, and then what's that going to do? Well, it's going to, I have to take that 419 kilojoules and divide it amongst all the photons that are required. All the photons that are required is a minimum of 6.022 times 10 to the 23rd photons. And this is going to give me the amount of kilojoules per photon, but it turns out it's an extremely small number, so I'm going to change it to joules per photon. So what I'm going to do here is I'm going to go 419 divided by 6.022 times 10 to the 23rd, and that gives me 6. Then convert it to joules. So times 1,000. And that gives me 6.957 times 10 to the minus 19 joules per photon. And this is going to give me potassium plus an electron. All right, now that I have this, then I can plug this in. E of the photon is equal to 6.957 times 10 to the minus 19 joules per photon, which is equal to hc over lambda. And so lambda is just going to equal hc over E. And so let me invert this times 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8 meters per second. And this gives me 2.855 times 10 to the minus 7 meters, which is equivalent to 285.5 times 10 to the minus 9 meters, which is equivalent to 285.5 nanometers. So what kind of light is that? UV. So the point of this problem is to illustrate that be careful with what energy you use. Are you using the total energy or are you using the energy of the photon? When we do these calculations, we have 2 energies that we deal with, and we have to make sure that we use the correct one. All right, so when we heat up these metals like this, the electrons get excited. When electrons get excited, they don't stay excited forever. They start emitting light And depends on how excited they are. If they're a little bit excited, they'll emit infrared. The more and more excited they get, they'll start emitting infrared, then red, then orange, it gets yellow. And the more green, blue, indigo, violet, the more white the light turns out to be. And so if we look at the emission spectrum of a black body, this is a black body emitter. What type of radiation is this? 1250, 1000, 750 nanometers? What kind of radiation is that? Infrared. So we start emitting in the infrared. As it gets hotter and hotter, let's say 5,000 Kelvin, we start to see what type of light is this? Visible light. Visible is between 760 and 390. So we're starting to emit visible light and a little bit of UV. And then as we get hotter, 7,000 Kelvin, we're going to start emitting a lot more visible light and then significantly more UV. And so this is a black body emitter. Black body, this would be glowing white hot here. And this would be glowing white hot here, but it would have more red to it. Because we're at, whereas this has a lot more blue, indigo, violet. And so this would be a cooler white temperature. This would be a warmer white temperature. White light. Okay, this is fine. This is what we expect for black bodies. So the physicists did some calculations. And the physicists, when they did the calculations, they expected as electrons get more and more excited, we should start emitting more and more UV. But what happens is, and this is Newton's law is what we call classical physics. Newton's law predicted that the UV intensity will grow as we get hotter and hotter. But it didn't. It didn't quite grow as expected. And this resulted in the first failing of classical physics. And the first failing in classical physics is called the UV catastrophe.
Dramatic, aren't they?
Yeah. It was a catastrophe because, it was so successful. Newton's laws were very successful. That was totally unexpected that it would fail. And so why did it fail? Nobody knew exactly why it failed. But somebody came along and tried to modify Newton's laws. And that somebody that came along that modified Newton's laws is this guy, Max Planck. And Max, with a C, CK. Max Planck came in and he said that energy, like matter, is discontinuous. Energy comes in packets, and these packets are h nu. And so what you do here, what he did was this. When we say discontinuous, we mean quantized. So energy is quantized. And so what we do is we modify Newton's laws to account for quantization of energy. Newton's laws are classical physics. And the Newton's laws have been around since the 1700s. Have they? Yeah, 17. And so we modify Newton's laws using this. And then the math works. So with this modification, then there's no longer a UV catastrophe. With Planck's, we expect this decrease in the UV.
I thought I was so worried.
Math fits. But that means we have to look at light and energy differently. And so what do we do in this case? What we do in this case is this. When we look at the electromagnetic spectrum, is it discontinuous or is it continuous? So I'm going to go from low energy to higher energy, Roy G. Bibb.
You're giving all of the calculus people flashbacks, just so you know.
Flashbacks to,
Continuity.
okay, that's. In other words, do you see all colors of the rainbow or are some colors missing? when you looked at the spectroscope yesterday, did you notice any black gaps in the rainbow, or did you see all the colors smoothly transition from red to violet?
It depends on what you looked at.
No, just looking at white light
Oh, no.
or the solar spectrum. It's continuous. Not only is it continuous in the visible, it's continuous in the IR and the UV. It's continuous. And so the question is, what the heck is he talking about? Energy is not discontinuous. Energy is continuous. And so what's Planck talking about?
I don't know, maybe just
What Planck's talking about is it's discontinuous in another way. And the other way it's discontinuous is red. Can you have any energy of red light you want? It turns out you cannot have any energy of red light that you want. You could have 1 photon's worth of red light, but can you have 1.5 photons worth of red light? No, that's impossible. So it's discontinuous in this sense. However, we can have slightly higher energy of red light by decreasing its wavelength. So we can have any color of red light, but with each of these colors of red light, then it's discontinuous here. And the same thing goes with violet light over here. With violet light, we can have 1 photon's worth of violet light or 2 photons worth of violet light, but we can't have anything in between, but it's continuous. We can have any size ball, but once you pick a size ball, then you can have 1 ball, 2 balls, 3 balls, but you can't have it. So it's continuous. Any size ball is allowed. Any size ball is allowed. And therefore, it's continuous. However, once you have a specific size ball, then it's discontinuous. Here it's quantized. So that does a weird thing to the energy, you know. Of course, we can have any energy of light we want, from low energy light to high energy light. But once we have that specific energy of light, then it's quantized. So when we're looking at red light at 760 nanometers, we have 1 photon, 2 photons, but we can't have anything in between. And so by accounting for this, then the UV catastrophe can be modeled. And so this is quantized here. I'll just point it here. These packets are called quanta of energy. Okay, so what we're going to look at a little bit more is the photoelectric effect. And so the photoelectric effect here is knocking electrons off the surface. And so it doesn't matter what the total energy is. What matters is the photon energy here. And so when we look at it, there's going to be a certain threshold photon energy required to knock off the electron. That would be it. And so it depends on the size of the ball. So once that ball hits, we can eject an electron. And then there are a couple of more things to say about that, but I'll say about it next time. We'll stop here. Tomorrow's lab is going to be very busy, so come semi-prepared.
I'm sure somebody we did a book for it's come on time, guys.